All righty, good night. Or good night, I'm already saying good night. Good night, good evening. Wow, well, thank you. Welcome to our fourth and final lecture in our spring series. Did you miss me? I guess the answer is yes. That's pretty awesome. Thank you, I appreciate that. For those of you who don't know who I am, I'm John Mulcahy. I'm the director of the Carnegie Observatories. And I've been serving as one of the co-interim presidents for the Carnegie Institution. So that's why I've missed the last two lectures. I've been going back and forth to DC pretty much every other week. I'm leaving tomorrow morning, and I'm thrilled about it. I'm on the airplane a lot. Anyhow, the good news is we do have a new president. So for those of you who have not heard, so I'm very excited about this. His name is Eric Isaacs. He's from the University of Chicago. He's a physicist, so that's always exciting for us astronomers. And he at Chicago, he's been working on partnerships with the university, and one of those partnerships is actually with Carnegie. Chicago is a partner in the Giant Magellan Telescope, which is, of course, a telescope that started at Carnegie and we're playing a part in. And so that's very exciting. So he'll be here on July 1st, and then I will be back full-time in Pasadena. So I'm very excited about that. So yes, and we're very excited to have Eric. So you'll see him at some point, probably next year. We'll have him come out for one of the lectures. I want to take this opportunity, since this is the final lecture, to provide all the thank yous for the people who really put a lot of time and effort into this. First, I want to thank the staff of the Huntington, and the volunteers. These are the people these ushers that help you every time take care of the process. We really appreciate them and allowing us to use this beautiful hall here. I want to thank the volunteers at Carnegie. It takes a lot of effort. All those people who check you in are Carnegie volunteers. Some of them are postdocs. Some of them work on our admin staff. And they're volunteering to help every year with this. So that was really, really great. And I also want to thank the Norris Foundation, which is a local foundation here in Southern California that provides the financial support for the series. So we greatly appreciate them. Now, although this is our last lecture until next year, at least as part of this series, I do want to let you know that our friends at Mount Wilson have a new lecture series that we wanted to advertise for them. So if you would like to continue to hear about astronomy in the coming months, over the summer months, you should check out the folks at Mount Wilson. And in addition, they also have the concert series that they've been doing for a while in the 100-inch dome, which is really great, the dome where Hubble effectively discovered the universe. And so those go on throughout the summer too. And so if you want to find out about those, you can visit mountwilson.edu, and we encourage you to do that and continue to learn more about astronomy. And I also wanted to point out, for some of you who may not know, we've launched a new newsletter at the observatories, Carnegie Observatories. It comes out 4 times a year. This is a way to keep track of what's going on in astronomy in our department and elsewhere. And so if you haven't signed up, those are electronic newsletters. Please make sure you sign up to our newsletter on the way out. Okay, so that's kind of some of the background stuff. As many of you know, 2017 was a particularly impressive year at Carnegie Observatories. It was a very exciting year to be the director, because really more exciting discoveries happened last year at the observatory since, I would say, the time of Hubble in the 1920s. You'll be familiar with the most distant black hole that was found. You'll be familiar with maybe the zombie star. It was a really kind of fun press release we did in the fall. But the biggest result of all involved tonight's speaker. And so this was the discovery of light from for the first time of a merger of 2 neutron stars. This is the fabulous picture that we had done for our press release, which you see all over the place. You're going to learn more about why that was such an exciting discovery from tonight's speaker. But let me say that one of the really interesting things about this discovery is that this was the first time we've been able to use light, the traditional tool that astronomers use, and a detection of gravitational waves, which was done by our colleagues at Caltech and MIT with LIGO. And this combination, this is what we call multi-messenger astronomy. This is a brand new field, the ability to use 2 different techniques to study an object. And this is an extremely, very exciting work. And we're very happy that at Carnegie we played a key role in that. It was our Las Campanas Observatory where the first light from a neutron star and neutron star merger was ever detected. And Maria was one of the first individuals to see that. So that's very exciting. So now let me actually introduce Maria. So Maria Drout is a Hubble Fellow at Carnegie. And she's also the very first Carnegie-Dunlap Fellow. Dunlop is an institution at the University of Toronto, so she has a joint appointment between Toronto and Carnegie. She received her master's from the University of Cambridge in 2011 and her PhD in 2016 from Harvard. Very unimpressive. And Maria is an expert in lots of different things, but particularly exploding stars, supernova explosions, all sorts of exotic, we call it transient. These are things that kind of change over short time scales. as well as the population of massive stars. She does some really interesting and exciting work that you're going to hear about today. And finally, let me just say that one of the things, and I say this over and over and over again, one of the great things about Carnegie, being a postdoc fellow at Carnegie, is that this is a great launch pad to a career. Almost all of our fellows go from here to being faculty members at universities. And we're very, very proud of this fact. It really is the best program in all of astrophysics. If you want to get a job, if you want to be a faculty member somewhere, you want to be a postdoc at Carnegie. And Maria is no exception. So I'm happy to announce that she is going to just start in September. She'll be an assistant professor at the University of Toronto in the Department of Astronomy. And so this is very exciting, so we're happy for her to do that. But the nice thing is we were so impressed with her that we've decided to continue to keep her here part-time. So she'll have a joint appointment at Carnegie, at least for the next year or two. And so this is something we're very, very excited about. Okay, so I've talked a lot, but let me introduce, after all that, Maria, no expectations, Dr. Maria Drout. Let's welcome Maria to the stage.
Excellent. Yes, thank you very much, John. No pressure whatsoever based on that. So yes, I want to thank you all. I'm actually embarrassed to say that after almost 2 years of living in Pasadena now, this is actually my first time at the Huntington, although it had been on my list for a while, so I want to thank you all for the very warm welcome. And today I'm going to be talking to you about astronomical alchemy, the origin of the elements. Now, I'm guessing since most of you are here, you're not like super scared by a little bit of chemistry, but I promise this will actually be mostly an astronomy talk, and as you can see here from the background picture, it will have a pretty explosive ending as we're sort of going to be building up towards some of the results from the neutron-star merger that John mentioned in his introduction. So I always like to start these things, though, by trying to give you a bit of a piece of where I and my research falls within all of what I'm going to talk to you about today. So I like massive stars. Now, don't get me wrong, the sun is great, especially the whole facilitating life on Earth thing, but I enjoy thinking about stars that are at least, 10 times bigger than our own sun. It turns out that how these stars evolve and change over their lives, as well as in particular how they die at the end of their lives, is very important. And sometimes I study them by looking at the stars themselves, by looking at fields in nearby galaxies like this and studying populations of stars and what their properties are. But a lot of the time what I do is slightly more dynamic. I study explosions. So much of what I do can fall in this field of time domain astronomy, and here's how you should think about this. Much of observational astronomy is essentially static, operating on time scales much, much longer than the typical human lifetime. So, for example, people who study planets don't actually get to sit there and watch a planet form. People who study galaxies don't actually get to sit there and watch two galaxies merge because the time scales involved are millions, if not billions of years. However, there are some aspects of things that happen in the universe that do happen on time scales of days to weeks to months. And those things include explosions. In particular, the catastrophic deaths of massive stars at the ends of their lives called supernovae. Now, as it turns out, these massive stars and their explosions are incredibly important for almost every area of astrophysics. And I'm not just saying that because I study them. And I'm also saying that despite the fact that they're relatively rare as stars go. So for example, if you wanted to find one star that is, say, 15 times bigger than our own sun, which seems pretty big. It's actually pretty modest. We know of stars that are 30 to 40 to 100 times bigger than our own sun. But if you wanted to have one of those, you would need to look in an area that also contained about 550 stars that are similar to our own sun. So much, much larger. And if you go even smaller, that same region, if you want, again, just one massive star, you would need something like 3,000, or the region you're looking in would be like 3,000 stars that are smaller than our sun, known as M dwarfs. I actually got sick of copying and pasting, so that's not actually to scale. But it's just to show you that these are relatively rare objects. However, they have a very outsized influence on the environments around them. For instance, they are incredibly bright. They also have incredibly strong stellar winds. So our own sun has a stellar wind. There's material flying off of it all the time. This is what creates the aurora when it impacts the magnetic field on Earth. Massive stars also have winds, but they are constantly losing millions of times more material than the sun is at any given point in time. So an incredibly intense amount. So between these winds and their radiation, they affect everything around them. Third, though, massive stars, through their deaths as supernova explosions, actually create black holes and neutron stars, which are another very dense type of stellar object, about as close as you can get to being a black hole without being one. They're very important for people who study fundamental physics, especially people trying to understand general relativity, and it is massive stars through their explosions that actually fundamentally create them. They are what's left over afterwards from the supernova explosion. And finally, the most important thing for this talk and how I'm pitching it, massive stars, through both their lives and their evolution and through their deaths as explosions and other sorts of catastrophic things that happen to them besides normal explosions, just if you want to get weirder, actually create almost all of the elements in the universe. Everything that galaxies are made of, everything that the Earth is made of, everything that we are made of. And Carl Sagan actually put it the best, so I'm going to put up the quote. "The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff." This is an incredibly profound and poetic statement. It's also one that's incredibly nuanced. After all, there are many ways, actually, that elements are made in the interiors of stars. Each individual element has its own origin story. Some of them are in the interiors, some are in the explosions, some require exotic explosions. And so that's my plan for this evening, is to try to walk you through this. How do stars actually make elements? And in particular, how do we, as astronomers, I am an observer, how do we actually know that, or think we know that that's true? So I'm going to walk you through that. That's sort of the plan for this evening. And we're going to end, the final part is going to be the most recent piece of knowledge we have to this, which came from the neutron-star merger last fall, which informed our information on some of the heaviest elements in the universe. So first things, we want to make sure that we're all talking about the same thing when I tell you we're going to talk about elements. So these that Carl Sagan mentioned, these are all elements. So what is an element? It has long been known, pretty much since ancient times, that there are different materials on Earth that have different physical properties. At the time of Aristotle, it was thought of as these four elements. You have earth, water, air, and fire. However, even in the mid-1600s, well before we had a complete theoretical understanding of what an element truly was, there was a much more technical definition where it was understood that there are different materials that have unique properties that are somehow more pure and cannot be broken down into any other constituent elements. Now, of course, since sort of the early 1900s, we have the following understanding of what an element is. Elements are made of protons and neutrons, and these together form the nucleus of an atom. And those atoms also have electrons around them. And this is what defines a given element. What defines it is intrinsically the number of protons, so the red ones in this diagram. How many protons are there in the nucleus? So a different element can have slightly different numbers of neutrons or electrons, but it remains fundamentally the same element or compound based just on the number of protons. So this is hydrogen. It has 1 proton in it. This is an example of helium. It has 2. And this is iron. It has 26 protons in its nucleus. You can combine different elements to make different compounds. So steel is made of iron along with carbon and other elements. But fundamentally, these are the building blocks of chemistry and therefore also of life here on Earth. So when you piece everything together, this is the periodic table. You're going to see this a few times throughout this talk, although I promise it's an astronomy talk, not a chemistry talk. So this is the periodic table. This is just lining up all of the elements that we know now by the number of protons that are in them. So 1 up here at the top is hydrogen, and helium over here, and just counting all the way down. When you line it up like this, it's nice because different elements with similar properties line up next to one another. There are about 118, 119 known elements. 90, some of them occur naturally on Earth, and we have measured about how much of them there are. So where do these elements actually come from? To start to answer this question, we have to go way, way back in time, and way, way before most of my expertise with massive stars was relevant. This is a timeline of the universe. So we are here at present day. This is clearly an illustration. So as you go back in time, you go through life begins on Earth, you go further back, the solar system formed, further back, the universe begins to accelerate, further back you have sort of the first stars and galaxies, but we need to go back even further, all the way back to approximately the first 3 minutes of the universe. And this is when the first elements were formed. So how does this happen? I'm about to show you an incredibly simplified characterization of what we think happened during these first 3 minutes that the universe existed. First, in the first millionth of a second, the universe is just this hot primordial soup. It is a bunch of particles whizzing around. It's so hot, in fact, that not even protons and neutrons can hold together. It's much more fundamental particles than that. By about 100th of a second after the Big Bang, it's slowed down a little. You can think things are slower. It's cooled off. You still can't form elements, but now your neutrons and protons are actually holding together. By 14 seconds, you still don't have elements. It's still too hot for that. They disintegrate almost immediately. But now you start have processes where protons and neutrons can sort of swap with each other. So how many protons compared to neutrons is changing, which turns out to be relevant for what elements you can actually form. And it's about at 3 minutes. 3 minutes after the start of the universe is about when we think that the conditions were cool enough such that you could start to form actual elements. You started to form hydrogen for the first time, where you had a proton and a neutron joined together. And then some of them would run into each other and start to form helium. And our understanding is that from about 3 minutes to 10 minutes after the Big Bang was when this happened. And then after 10 minutes, it was too cool already, so no new elements could be formed. So that's pretty quick, as initial conditions go. And this is our understanding of sort of, as a result of after that, what the universe was made of. About 75% of what was there was hydrogen, of the elements that is, about 25% helium, and less than 1% lithium, and a few other things. So you might ask, so how do we know this? I told you I was going to tell you how we know this, and it is a good point. We cannot see this part of the universe. So a lot of what I just described to you is theoretical understanding, where we try to take our knowledge of what the physical conditions must have been, and therefore what would happen. But we have several lines of evidence. For instance, when we look at the universe today, you see about 75% of the elements are hydrogen, about 25% are helium. And you can get more nuance than that, but this, at least on that basic level, seems to make sense with what we see in the universe around us. So, how are we doing on our periodic table? Not great, huh? So we didn't get very far, and I'm even sort of charitably giving us beryllium on this diagram. So, although, people actually make fun of astronomers a lot, saying we mostly do things order of magnitude as compared to very precision science done elsewhere. And order of magnitude, we've got everything. At least in terms of mass and number of elements that there are. So we could be cool now. We could be done. Except you might notice a few rather important elements, at least for life here on Earth, are missing. In particular, almost all of what we're personally made of and almost all of what the Earth's crust is made of has not been formed yet. So clearly we need to understand, how do you take these initial conditions where you have a bunch of hydrogen and helium, and how do you make new elements? When you have some elements and some other constituent parts, but how do you put them together? Turns out, it's super simple. You just need this big red stone, and all of a sudden you have gold. Right, Harry? Okay. So that was clearly a joke, but in all honesty, I actually think the history of alchemy is fascinating. Many of the alchemists were actually some of the earliest chemists. They actually did discover some of the first chemical reaction and ways to put different materials together to produce new compounds with different properties. However, they were somewhat fundamentally flawed, although they didn't understand at the time. When they were trying to do things like make a philosopher's stone or somehow other convert things like mercury into gold, what they didn't understand is there is a difference between the other changes than they had been able to do, which were chemical, and what they were trying to do. Namely, gold and mercury are elements. In order to change between one of the others, it's not a chemical reaction. You actually need to get into the nucleus of that atom and change it. And it turns out that's way, way harder to do. So for example, this is what modern-day alchemy on Earth looks like. This is a nuclear power plant. Nuclear power plants are doing alchemy. They are taking certain elements and creating new ones from that, putting energy in and getting energy out. So what's important is that to actually get into that nucleus and change from one element to another, you need such high temperatures and pressures and densities, it's almost impossible to create them here on Earth. But there are places in the universe where this does happen. For instance, the interiors of stars. Turns out stars, they're pretty big. They've got a lot of gravity that's pulling inwards on them. And as a result, you have very incredible temperatures and pressures on their interiors. So for example, our own sun, it's something like 5,000 degrees on its surface. That's what we see. Down in its core, it's something like 27 million degrees. That's how hot it is in the center of the sun. The pressure in there is something like 250 billion atmospheres, so where the atmosphere is the pressure on us from Mars. That's what the conditions are in the center of the sun. And that's enough, just from the gravity pushing in on it, that's a high enough temperature and pressure that the hydrogen the sun is made of will start fusing together to make helium. It just happens in those physical conditions. And that's actually really good for the sun, because when that happens, you actually get energy out. Hydrogen turning into helium gives you energy, and it's the energy from that process that actually supports the sun against its own gravity and stops it from collapsing. So that is how stars do fusion and create new elements. As it turns out, the sun isn't going to go much past that, but the heavier the star you get, the more and more elements you can make. And that's because once you go through and you get through all of your hydrogen, you have a core that's now helium. It's not going to make new helium, that's what it is. So the star will start to collapse in on itself, and it will push down even more. And if it's heavy enough, you might get to a higher temperature and pressure, where suddenly you start taking those helium atoms and pushing them together until you make new elements from that. So this is just somewhat technical plot, but this is just showing you the density in the center of a star and the temperature. And now you should look at one of these lines, and this is time. Just think of a star in time going this way. So basically, as time goes on, it's going to get denser and denser and hotter, and at different points, different types of fusion will start to occur, and you'll create new elements. The heavier the star is, the higher up this chain you can go, because you will keep having enough pressure pushing down from its own gravity that you will create heavier and heavier elements. So for massive stars, the sun isn't going to do this, but for very massive stars, like the ones I study, you end up with sort of this onion-like structure, where you have hydrogen and helium on the outside, and you go all the way in with different elements you've created until you get to iron in its core. And it turns out that's actually as far as you can go, because once you get up to iron, actually pushing together multiple iron atoms to create new elements would start to take energy as opposed to give it. So this whole balance between, you have gravity pushing inwards, but you create energy from fusion that pushes outwards, totally breaks down. So you wouldn't actually be able to support a star based on that. So this goes up until iron, and that's actually as far as you can get. So again, I'm trying to tell you I just told you a nice, pretty story, but how do we know that that's actually true? We see the surface of stars. How do we know what's actually going on in the interior? It turns out that we do know for sure that fusion is happening in the core of our own sun, and that's because we actually detect neutrinos here on Earth, which are tiny little particles that are also created in that same process. And we have detectors, some of which are beneath Antarctica, some of which are in mines scattered throughout the world, that actually detect neutrinos from the sun and tell us that that is what's actually going on in the core. However, for massive stars, there's no massive star close enough to us that we can look for neutrinos in its core. So it is more indirect than that. We think we understand the physics well enough to know that this should happen, but most of our understanding that it is comes from comparing populations of massive stars and sort of predicting what we think the surface should look like as it's moving through this process, because it will change. So much of it actually comes from a slightly more indirect method than what we've been talking about so far. So we're doing a little bit better now. We are farther up the periodic table. We got all the way up to iron. So we covered many of the most important ones that we're made of, the Earth's crust is made of. Although there's this tiny little caveat that you actually, if you want to make a planet out of them, you have to get it out of the center of the star. So we'll get back to that later. But just bear with me. But for now, we have made those elements. They're just trapped in the middle of massive stars at the moment. But there's also several elements that are still missing. Maybe they don't make a huge fraction of what is here on Earth, but they're still important. So for instance, you do have things like, gold and other precious metals that some people think are important that haven't been created yet. But you also have things like neodymium, which is used to make magnets. It's in most of your speakers and most of your computer hard drives, and it's necessary for that. And then you even have things like uranium and other sort of very heavy and radioactive elements, which maybe it's not wholly good, but also there are trace amounts of uranium in the Earth's crust and in the mantle that actually heat the Earth and are probably partially responsible for plate tectonics, which might be partially responsible for life having evolved on Earth. So it turns out that many of these elements that we still have not formed are very important. So where do they come from? I just told you can't make them in the interiors of stars, which are some of the most intense physical conditions that exist in the universe. So how do you actually make the most heavy elements, elements that are heavier than iron? So fun fact, you can turn a neutron into a proton. That turns out to be very important. This is a process, we call it beta decay, but it's basically what it sounds like. Sometimes a neutron can just turn into a proton. It's going to emit an electron and a neutrino at the same time. And this is important because this can help you change what element you are. So for example, you can sometimes have an element that if, maybe you don't need to undergo full fusion, but if you have neutrons that are getting close enough, we'll go back and do this again. If instead of needing the physical conditions for fusion to occur of these heavy elements, if instead you just have a condition where sometimes another stray neutron gets close enough that it can get into the nucleus, initially you're not changing what element you are. We're keeping track of protons and neutrons here and what element you actually are. We'll go back one more time here. So you sometimes capture these neutrons. You're still the same element as you're doing that, but then every once in a while one will undergo this process. And then suddenly, you're not iron anymore, you're cobalt. Cobalt's heavier than iron. That was exactly the process we were talking about, how we need to get past that iron somehow. So this turns out to be very important, that sometimes in slightly different physical conditions, you can undergo this process where neutrons sneak into your nucleus, and then they can change and actually change what element you are. There's a couple different ways this can happen. This was an example. It says slow here. It's slow. So the idea here is that sometimes this happens where you don't have that many neutrons running into your elements, but every once in a while one gets in, and then every once in a while it will change, and you'll slowly creep your way up to heavier and heavier elements. But you can also have a situation where, let's just say you had a lot of neutrons around. You could undergo a process where a bunch of them are starting to glom on all at the same time. And then eventually one goes off. You'll notice again, we're still at cobalt, but it's a slightly different type of cobalt. And you might imagine that you end up with slightly different types of elements depending which of these you go through. Again, astronomers and other types of physics are great at naming things, so we call this the slow process and the rapid process as two different ways that this happens. So here's just another diagram to sort of illustrate this for you. Here you have, this is proton. So this is just what element are you going up vertically here. And here is how many neutrons do you actually have. And this black line is sort of where elements tend to be stable. They tend to be stable when they have similar numbers of neutrons and protons. If you've got way too many neutrons, they'll tend to undergo this process where they change what's going on in their interiors. So for that slow process, you're just sort of slowly meandering your way up, where you might capture a neutron and then sort of, it'll decay back down. So you're just going to slowly wander your way up this black line here and create heavier elements that way. However, if you have a rapid process, you're going to do what this diagram is about to show you. Instead, you're going to shoot way up and then decay back down. So here's what the rapid process looks like. Look at the colored diagram, or the colored dots. It's showing you where different elements are. So they suddenly capture a ton of neutrons, and then at a certain point, they start to decay back down. This is what this process looks like for how you would go from having fewer, we'll watch it one more time, sort of less heavy elements to heavy elements. So you sort of capture a bunch of neutrons to go up, but then at a certain point, those are unstable, so they're going to undergo this radioactive decay and fall back down. And you see you ended up with much heavier elements than you had when you started. So these are two different processes that were theorized and calculated, this slow process and this fast process. It actually turns out that we know that both of them happen. There's a couple of ways we know this. One of them is actually meteorites. So meteorites fall onto Earth every now and again, and they represent examples of pretty pure space rocks that haven't been contaminated by things on Earth, and we can study in very great detail. You can study in great detail sort of how much of each type of element is there and how much of each type of element with each number of neutrons are there. So you can actually create maps like this that take what is the atom and sort of how much of it is there. So here, you have a ton of hydrogen and helium, but then you see as we get to heavier and heavier elements, there's less and less, but we can measure this very precisely. And when you do this, you actually come out with back-breaking out that you need both the slow process to happen, but you also need the rapid process to happen, because you get slightly different elements out at the end. At least that's our prediction. So you actually need both. So it turns out that for the slow process, this can happen just in stars, just sort of in the atmospheres of stars. There are occasions where, once every 10 to 100 years, a neutron wanders its way into a nucleus, and this happens. And that's fine. So this slowly happens in envelopes of stars. But in order for that rapid process to happen, we're not talking you need this to happen once every 10 to 100 years. In order for that to happen, you need something like 100 neutrons a second hitting that nucleus. That's a lot. So that's okay, here you go. This is a slow process. That drop, that's a neutron about to fall into the nucleus. This is the rapid process. And this actually might be understating the difference between these two things a bit. You might need to even make something way more intense than this to represent actually just how many neutrons you really need being flung at these nuclei to make this rapid process happen. But we know that it does happen. So what's a situation in space where you have a ton of energy, but also way more neutrons flying around at these intense energies than you have in the interiors of stars? That would be explosions. So that's where we're going to get to now. This is how we're going to try and figure out where this rapid process is happening, how we're actually getting these heavy elements. And it turns out about half of the heavy elements, half of the elements heavier than iron, need this rapid process to happen. They have to happen somewhere other than just in the envelopes of stars to make it happen. So where could this happen? First bet, one of the most common types of explosions in space, a supernova. So this is the catastrophic death that most massive stars undergo. So once they get to that point where they have iron in their core and they just can't support themselves against their own gravity anymore, they will start to collapse in on themselves. And they will collapse in so much that it actually triggers an explosion, like what you saw here. These explosions are so intense that they actually throw several sort of solar amounts, so imagine several times the amount of material in our sun. It throws several solar masses outwards at something like 1/10 the speed of light. And when it's doing that, that's such an energetic process that you actually take all those elements that you synthesized in the core before and you completely disintegrate them. So I hope you weren't fond of those particular iron elements themselves, because they'll be completely obliterated. But as those then particles are thrown outwards in this intense explosion, it will actually create new elements, a process known as explosive nucleosynthesis. So these supernovae are incredibly bright. They're something like 1 trillion times brighter than the sun. They're going to outshine the entire galaxy in which they sit for a period of months. Or this is my absolute favorite analogy made by the Randall Munroe, who writes a webcomic called XKCD. He pointed out that if you took a supernova at the distance of the sun, it would be about 1 trillion times brighter than a nuclear bomb on your face. So quite bright. And it turns out that the energy in that light is still only a fraction of the total energy in these explosions. Something like 99% of the energy in supernova explosions actually comes out in these neutrinos, these very light particles that move at very high speeds and interact with almost nothing. Several neutrinos just pass through your body, as I just said those few words. And something maybe like 1% of the total energy in these supernovas coming out in actual motion. So like the energy of that material being flung out at these very high speeds. And only 0.01% is actually coming out in the light that we physically see. So this is that's my favorite 0.1%, because as an observational astronomer, most of the time this is all I have to work with. So you might ask then, okay, again, you just told me this nice story where supernova happen and they go off and they synthesize new elements, but especially since you can only look at 0.01% of what's actually going on, how do we know that this is actually true? There's a couple of different ways, but you're also right. So this is what a supernova looks like to us most of the time. You can see this source here getting brighter and then fainter. That is a supernova that went off back in 2011, actually in a very nearby galaxy. So this is one of sort of the best case scenarios. You have a dot, and if you're lucky, you have a dot in a beautiful galaxy as opposed to a dot on a smudge on one of your images. So we're trying to use this to disentangle things like, okay, were there actually elements synthesized in these supernova explosions, and what types of elements were there? But there's a couple of pieces of information at our disposal to learn about those things, in addition to other things about the explosion. So the first is just that it turns out a lot of these elements that are synthesized in the explosion are radioactive. So this is an example of what that supernova looks like to us. So here you saw it getting brighter and then fainter. So this is just a map of that over time. So supernova is getting brighter and then fainter over a time period of a few months. And it turns out, you might think, okay, when an explosion goes off on Earth, it is very bright, but only for a period, a few seconds, a few minutes, and it's because it's something very hot that emits a lot of light that you see. And something like that happens in supernova as well, where you have this initial flash of light, an initial bit of cooling because the material is just very hot from this explosion going outwards. But that only lasts a couple of days as well. The reason that this lasts for so long is that because you created those radioactive elements in the explosion, and those are continually injecting energy into the material you see. So we can actually map this out. For instance, most supernova that we see are powered by things like the radioactive decay of nickel into cobalt and then cobalt into iron. And it very closely matches the decay rates that you expect for those elements. So we can use things like how that light changes with time to measure both what radioactive elements are present, and in particular, because we think we understand that radioactive process, how much material had to be there to make it this bright. The other thing that we can do with supernova is look at their spectra. So this is taking that dot of light I showed you in the previous image and breaking it up into all its colors. So this is just showing you here, this is like the very blue light from this supernova, and this is the very red light. And this is just, again, brighter over here. So these are two different spectra of two different supernova. So you can see here, okay, there's sort of an overall shape, but there's also all these pretty prominent bumps and wiggles and features. And it turns out that those are due to individual elements that we see in the spectra of the supernova. So we can actually trace them back and understand what some of the elements that were present in the supernova are. So in particular here, you have things like these are due to hydrogen, which makes sense because a lot of massive stars, they still have this big hydrogen envelope left over when they go off. This is a different one that didn't have any hydrogen, but has things like silicon, sulfur, magnesium, iron, and oxygen. And you can see lines from those and piece back information about how much of those different elements had to be there. Now, so some of you may have noticed, oh, these elements you just listed, all of them seem like pretty small elements. I didn't notice any higher than iron in anything you've told me about so far. And that's actually, for the most part, true. It turns out a lot of the elements we actually see when we look at supernovae are some of the same ones that we thought should form in the interiors of stars to begin with. And this makes sense with the physical conditions we think understand happen within supernova. You do get a little further up, but in general, some of the most common elements that are created in this explosive nucleosynthesis that happens are still only going up to around iron, or something we call the iron peak, which is generally around this region here. So this doesn't mean that supernova aren't creating heavier elements. In fact, if you take the amount of these heavier elements that we know exist, at least based on our measurements in the solar system, and said, okay, let's say every explosion of a massive star created some of these, you would only need a very small fraction of material to be created in each explosion. So this is both good and bad. Good because you don't need to be able to make that much of it in every supernova to explain what you see, but bad because there's essentially zero chance you'd ever actually see it. Because the observed signatures of that would be totally dwarfed by the several solar masses of iron that are ejected in that same explosion. So you'd never actually directly see it. So that means people have been pursuing a lot of other ways to try to indirectly tell whether some of these heavier elements were created in supernova. It turns out that theoretical models also have a little bit of trouble sometimes creating the physical conditions, that whole like waterfall on a flower conditions of the neutrons coming in to actually make these heaviest elements in supernova. Although I should point out that a lot of these same theoretical models of supernova also didn't explode until a few years ago. So that's kind of a problem. But no, it's actually just, it's a very hard problem. If you want to theoretically model a supernova explosion, put in all the physics and see what happens, it's a very hard and complicated problem to actually trace out. So we would love it if we could actually directly trace or see whether these elements were created in supernova, but we can't. So there, as I said, there are other things people are doing, but in the meantime, people have also been trying to understand if there are other places where these heaviest elements could be formed in the universe. And one of those is neutron star mergers. So neutron stars are the dead cores of previous massive stars. And sometimes, if you have two of them that get too close, spiral together, and merge, you'll create an explosion. That is what this was just showing you. So you have two neutron stars here. if you manage to have two of them close enough together that they will sort of spiral around each other and get closer and closer together and eventually merge, they will create an explosion. This is very promising if you want to create heavy elements for a few reasons. First of all, they're neutron stars. So I didn't tell you too much of what they are. They are sort of the dead cores of previous stars that have gone supernova, but you can tell in the name, neutron star. Most of them is made of neutrons. So if you take two of these and sort of spin them together and you saw material being flown off here, you are going to get physical conditions that have an awful lot of neutrons flying around very quickly in this explosion. So it's hypothesized, and people have now gone back and tried to calculate in detail, that they do think that if neutron star mergers occurred, they should actually create the physical conditions necessary for this very rapid capture, this R-process nucleosynthesis to actually happen. So it's beneficial for a couple reasons. First, we think these properties actually happen. Or we think the physical conditions required would happen here. There's a couple of downsides, though, compared to supernova. First of all, these are much rarer occurrences. So each one of these neutron stars was left over from a supernova. So first of all, you had to have a system where it wasn't just a massive star. You needed two massive stars next to each other, orbiting each other, kind of think Tatooine's planets, or like the sun around the Earth, except it's two suns. Then you need the first one to go supernova, so massive explosion. Remember, nuclear bomb in your face type of explosion. And then you still have this binary star. And then you need the second star to explode as another supernova. And you somehow need the two remnants left over from that to still be orbiting each other as opposed to being thrown off into space by those explosions. And then when that happens, you then need them to be close enough together that they will eventually get closer and closer and closer and closer until they merge within the time of the universe. So that's less common than just a supernova, we'll put it that way. There was also the caveat that until last fall, although we know of a few systems that have two neutron stars that are close enough together, until last fall, we had not actually seen a neutron star merger. So that was also awkward. But yes, but it is the sort of thing that if it was able to occur, you need it to create more than an individual supernova, but the conditions are probably ripe for that. So just the questions are, do we actually understand these mergers enough, and how often do they actually happen? Can they actually explain some of these heaviest elements? So you might ask, okay, so why haven't we just observed some neutron star mergers like you observed supernova? So one of them is that they're much rarer, but also they're much harder to find. So we observe supernova by looking at patches of the sky over and over again, usually with telescopes dedicated. We're just looking over and over again at the same patch of the sky to try and look for anything that changes. Our surveys are getting much better. We can now look at much, much larger portions of the sky at once. This is a representation of what the Zwicky Transient Facility, which is being commissioned by Caltech right now, the patch of the sky it will look like. So we're getting better and better, but we've always had to make decisions. Sort of, we can only survey so much area in so much time, so how do we optimize what types of explosions we're going to find? So for instance, as just an example, if this is what a typical supernova looks like, so again, this is brighter here, and it's getting brighter over a few weeks and fainter over a few months. That means if we were designing a survey, we might be able to do something like look back at the same patch of the sky every 5 nights or so. And then you'd get information on how bright it was like this, which is sort of plenty good to tell information about what's going on in the explosion. But neutron star mergers are not supernovae. They have way less material in them to begin with, and it's different types of material, so it's expected to look different. In particular, it should be much shorter, something like an order of magnitude, rising over a day, falling over a week. So in a lot of the surveys we did previously, you might get data like that. Or if it was cloudy one night, you might get nothing at all. So it turns out we just actually weren't good at looking for the types of explosions that you expect neutron star mergers to be. So we're getting better at this, but also in the meantime, we could use a little help. Another way of finding them besides our own surveys, especially if it turns out that we don't understand neutron star mergers or they don't create heavy elements at all, so you just can't see anything. And that's where LIGO comes in. So LIGO is, as John mentioned, it's a large physics program. It's the Laser Interferometric Gravitational Wave Observatory. So it's basically a bunch of lasers in 4-kilometer-long tunnels. There's a couple of them throughout the world at this point. But they are looking for gravitational waves, which is basically space jiggling due to very massive objects moving. So say, for instance, if you had 2 neutron stars spinning around each other really quickly, that would make space jiggle, and in a way that's exactly what LIGO is designed to try to be able to detect. So they could, for instance, we were hoping they would find one of these, be able to tell us where to point, and we could look for light from it for the first time. So LIGO has been working for decades to try and build up its detectors and get sensitive enough to actually be able to detect gravitational waves. And they first did back in 2015, for which they actually won the Nobel Prize last year. But when they first detected gravitational waves in 2015, it was not for neutron stars. It was for two very massive, these are black holes merging together to form another one, which is great for them. It was a beautiful detection, wonderful piece of science. The problem for astronomers is that if two black holes merge, you don't expect to see anything. They're both black. It's black afterwards. We looked anyway. We really did, but we didn't see anything. So for us, it would be much better if they were to, for instance, find a neutron star merger, but they hadn't yet. And it was not weird that they hadn't. So for instance, you can only see them much closer because they're lighter than black holes and things like that. So actually, a few very prominent scientists back of August 17th, 2017, a few weeks before that, had made some bets at a conference that it would be something like 3 to 5 years before LIGO saw a neutron star merger. But as it turns out, on August 17th, we got this telegram. Yes, this is actually what they send us, a plain text email, letting us know that the LIGO Scientific Collaboration and the Virgo Collaboration report, most of it's not important, but this is a candidate is consistent with a neutron star binary coalescence, so that means a merger, at a false alarm rate of 1 per 10,000 years. That means they think the noise in our detector means we would only detect something like this once every 10,000 years that wasn't actually true. And just for some context, they will report things to us with false alarm rates of once per year. So it's basically like, this is really significant, and also it is a neutron star binary. So this is the first time this has happened. So I've highlighted why this would be useful for nucleosynthesis and understanding the origin of heavy elements. There are many other reasons why this is very important, and especially if we can find light from it. If you can find light from the same type of event that you have gravitational waves from, you can do so many fundamental things. Things from studies of fundamental physics and GR, things to understanding the expansion rate of the universe, nucleosynthesis, understanding other things in astronomy, such as the origin of gamma ray bursts. All of this could be done if we could find light from this. And this came out, at something like 10 a.m. California time, and it quickly discovered that where it was in the sky, because they can sort of tell us where it is, but only a patch of the sky that's something like 150 moons. So we still had to search. So we basically figured out that it was going to be the observatories in Chile that had the first opportunity to look for light from this neutron star merger. And in particular, this is just a map of the entire sky, so projected onto a sphere. This is the blob where LIGO and Virgo were able to tell us where it was. So this is a size about 150 square moons on the sky. This dotted line is where we can see from Chile at night. So the important things to note are we were going to be first to be able to see it, but also this is kind of close to the edge there. So we knew, and we had about maybe 8 hours of warning, that we were going to have 1 hour in which to try to find this. It was going to be above the horizon at night when we can look for things from the sky for 1 hour at the beginning of the night. So we prepared as much as possible, sort of planning out exactly how we were going to map this out, looking at the brightest galaxies first in that region to try and look for new types of events. And it turns out we got lucky. We had an hour. It took us about 12 minutes. So what we show here, this is an old image of a region around one of the galaxies that was within that patch of sky. And this here is an image that we took that night. So yes, 12, 15 minutes after twilight ended at our observatory. You can see there's a new source that is not here. So that's very promising. But of course, that doesn't mean it's true. This was taken months previous. This could just be some other supernova that had gone off in the meantime. So we took a spectrum of it. And it looked like this. Basically, what I want you to take out from this is it's very smooth. It's pretty blue. For those of you who remember, this is sort of where blue light is. So this tells us that it's a very young source. So again, that's very promising because we knew that this was new. But again, it could just be like really bad luck, a very new supernova that exploded in the same region. So it was really when we went back the next night and we saw it looked like this. So this is like 24 hours later. Supernova don't do that. I'll just point that out. So basically, all you need to take away from this is it was very different already by 24 hours later. Supernova, again, they rise like somewhat slowly over a couple of weeks and decay over months. This was changing very quickly. So it was about then that we figured we had the right source. So in the end, something like dozens and dozens of observatories and a huge fraction of astronomers in the community observed this source from observatories all over the globe and many of the space satellites. And many of them were prompted by that observatory, that observation which was first done from our observatory down in Las Campanas. So now I wanted to spend a couple minutes telling you a little bit more about the story, though, because it was pretty intense that first night finding it, but as it turns out, the following week after was also pretty crazy. I told you that we expect these neutron star mergers to change very quickly, rise over a matter of day, and the light to be gone within a week or so. So that's what we were expecting to happen, so we had to sort of change things quickly. But as it turns out, this happened August 17th, and there was another very relevant astronomical event that was happening somewhat related. So we're going to play a little game of where in the world are the Carnegie scientists during this entire period, and for instance, the first week afterwards. So on the first night where this happened, there were 4 of us who were most prominently involved, along with several collaborators at the University of California, Santa Cruz, who were pivotal in this happening, but I'm not showing everyone's picture. So when this happened, 2 of our scientists, Ben Shappy and Josh Simon, were actually down at the observatory in Las Campanas on the telescopes, whereas myself and Tony Pirro were here in Pasadena. So what I'm showing you here is a map of where we are, and then this is what the explosion is doing over this time period. So what you should look at is just, so the blue is going to be blue light from this explosion. The red is very red, or infrared light, actually, from the same explosion over time. And again, further down here means it's faint. Up here means it's bright. So in the first day, after that first night, Josh flew back to Pasadena. Then at the same one night later, so it's already by one night in, it's like a factor of 10 dimmer than it was before, although it's still getting brighter in the infrared. And Ben is flying back, but you'll notice he's not actually flying back to California, he's flying to Utah, which will become clear in a minute why he's doing that. So at the same time, myself and another astronomer, Jen Van Saders, who gave one of these lectures last year, got in a car and are driving up to Utah to meet Ben. The reason why, again, will become somewhat clear. And again, throughout this entire time, we are coordinating all of these observations while this is happening. And we are camping this entire time, I will also add. So, as we were doing this to meet him in Salt Lake City and pick him up from his return trip to Chile, to go up to Mackay, Idaho, because it turns out the solar eclipse was happening. And many of us from Carnegie had an event that we were going to up in Idaho, including those of us who were most prominently involved in this. So again, we're already here. We just got there for the eclipse. This thing is almost already gone. This is like as faint as we can detect with telescopes. It's like a factor of 100 fainter. It's almost gone in visible light already just a few days in as we're driving across the country to do this. It's still bright in the infrared, though. That's pretty cool, and it's very interesting. So now you might think sane people at this point were like, okay, this is clearly a really big deal for like all of astronomy, so maybe we should just drive back and work. But this had been when Ben and Jen were taking their last vacation before starting as faculty members at the University of Hawaii and been planning to go backpacking in Utah for a week at national parks. So we decided we should still do that while continuing again to work. So we saw, arches, it's beautiful. Again, it's getting fainter, brighter here. Went and saw, Monument Valley here. Our colleagues in Pasadena are getting more concerned, but we're still actually doing the work at this point. I actually went to McDonald's to download data and then analyze it in my tent. I actually did that. That's a true story. As you can see, it's really almost gone in the optical now. And finally, we did Bryce Canyon. That was beautiful. Went through, and then finally, about 9 days later, after the event, got back to Pasadena after this adventure. You can see this highlighted region is when that happened. So it's almost completely gone in visible light. It's only in the infrared, which you need different types of instruments to see, that it lasted for a few more weeks. So really, some of the most intense parts were happening during this experience. And many astronomers were going to the solar eclipse, so many people have similar stories. So what does this all mean? This will just be the last few bits of the talk here. Why does this matter other than being monumentally cool? So you can see here, this transient again, whereas most supernovae get brighter over weeks, fade over months, this was gone within a week and maybe within 3 weeks in the infrared. This is unlike any other transient or explosion we have ever observed as astronomers. And it has very useful information in terms of this question of the origin of the elements. It was useful for so many different types of science, all the different things I listed to you before. But here I'm just going to focus on what it taught us in terms of the origin of the elements. So it turns out by modeling all the detailed light in the infrared and the visible light that we got from this, we conclude that you do actually form a significant amount of heavy elements in neutron star mergers. There are a couple different ways we did this, but I'm going to focus on the two that I also told you about for the supernova. So for instance, remember for the supernova, you can learn a lot by studying what the decay rate is and how bright it is because you have a lot of radioactive elements that are synthesized. Now, in a neutron star merger, you also synthesize a lot of radioactive elements, but you're not creating mostly one, whereas supernova mostly synthesize nickel-56. All of those elements up that chain are radioactive, but you can predict sort of ensemble what the decay rate of sort of a population of those elements, heavy elements, should be. And it turns out when you do that, you predict something that very closely matches what we actually see in terms of how it fades with time, indicating that it really looks like our process, radioactive elements were synthesized in the explosion. In particular, with how bright it was, a significant amount of them had to be created in this explosion. And second, we can look at the spectra. So before I told you as we break it up in light. So now this time, though, I'm breaking it up in light, but it's actually an infrared spectrum. So as opposed to visible light before, think of like an infrared image of something, but again, broken up into different colors. And you can see it's wavy like this. So unlike the supernova where you saw wavy features from individual elements, here there's so many elements there that all sort of fall on top of each other that you aren't actually seeing individual elements. We're unfortunately not seeing, oh, this is a bump due to gold. However, you can compare to models, the model is in red, with what you expect if you have an ensemble of these elements again, what should it look like? And it very closely matches what we see. So those are a couple of the reasons we now think we understand that these are process or these heavy elements are being created in neutron star mergers. There's a lot still for us to understand of the details of it, what elements exactly, how well it matches other observations. And for instance, if supernova can still be another site where they occur, we now know for sure that these very heavy elements in the universe are formed in neutron star mergers. And so this is what our periodic table starts to look like, where we're filling in things that were created in the Big Bang, things that are found in exploding stars, sort of up through this first level, and things which are formed both through in the envelopes of other stars, the S process, and then the components that are formed in things like neutron star mergers. And with that, I will take any questions. Thank you. Mm-hmm.
Okay, time for some questions.
So where is black matter in all this?
The question is, where is dark matter in all of this? Not in all of this, and that's the point. So actually, that's a good question. So this was about the origin of the elements, and our understanding, so when people talk about light matter or normal matter versus dark matter, the normal matter is elements, things that are made of neutrons and protons and other things, whereas dark matter is intrinsically something that is not that. Because if it were, it would interact with light and we would see it. So it is not in this picture. The question of where it formed is a very good one as well. That would need an entire other talk devoted to it, especially since it's still not known exactly what dark matter is.
The base elements that are then isotoped up to the higher, where are they on the neutron star? You have to start with base elements.
So you actually don't need to, and that's one of the cool things about this. So the diagram that I showed you that had sort of a base amount that then capture up, it showed it for illustrative purposes, but you can start with something like the neutron star merger, and you do have particles there. It's not only neutrons. You do have some protons and other stuff as well, but you can do it can also be what's called a primary site, where you can start from these particles and you create some very light nuclei up to iron and then go from there. So you don't need sort of very heavy elements already there on the neutron star in order to make this work.
If you were to sum all the total energy output from a supernova
That's a good question. So if you sum everything up for a supernova, it's something like, we use funny units, it's like 10 to the 53 ergs. It's quite energetic, and sort of the light from that is maybe, 10 to the 49. So the light coming out of the neutron star merger that we see is something like a factor of 100 less. So it's less energetic than a supernova, and even once you add back in sort of the energy with stuff being thrown out, the neutron star merger is less energetic unless you start including the energy that's released from. So the reason that they're merging is because of these gravitational waves that are being emitted outwards that then LIGO detects. So if you start including sort of the total energy from those gravitational waves that happened before the collision, they start to become comparable. Sure, yeah, so the question is sort of related to these two neutron stars. In order for them to merge, you needed two of them. And so the question was, do they have to be ones that have orbiting around each other for their entire lives, or can you have a situation where instead you have several of them maybe just running into each other for other reasons? And that's also, it's more debated for the black holes, actually. There's sort of a large debate going on in the community right now about where these very massive black holes that LIGO found merging, where do those come from? And there's sort of the debate of, do you need two stars that were massive enough to create black holes so big that have been in binaries their whole life? Or there are certain regions of space that have a lot of stars moving past each other all the time. So in most of the galaxy, it's very unlikely that you have two stars passing close enough together to collide. However, there are things known as globular clusters, which are clusters of stars that are very close to one another. And in the centers of those, you can have stars colliding into each other a lot. And it's thought that some of these mergers might be happening in regions like that. So not things that evolved together their entire life, but ran into each other later. Yes?
You mentioned neutrinos and being able to understand that these processes were happening. Neutrinos were detected.
Yes. Yeah, so the question was, I had mentioned at least at one point, and I could have mentioned at a different point, that we understand that these processes are happening. I think the example I gave here was we know that fusion is happening in the center of the sun because here on Earth we actually detect neutrinos from the sun. And yes, so basically based on the number of neutrinos, to a certain extent, based on the number of neutrinos you detect and what type they are, you can understand that in the sun it is hydrogen that is combining to form helium primarily, because you expect when that happens certain types of neutrinos to be emitted.
There are different types of neutrinos.
There are. It was actually this actually was understanding that there are different types of neutrinos, but then in particular that the types can switch between one another. I'm not sure which year it was, but it was awarded a Nobel Prize an earlier year because a lot of these detectors on Earth of the neutrinos only detect certain types. So for a while it actually looked like the number of neutrinos we were detecting from the sun was vastly different than the amount we predicted. So indicating that, maybe either fusion isn't happening, but we think it really is, but that means we don't understand hydrogen fusion, whereas once it was understood that there are multiple types of neutrinos that can change amongst each other, everything sort of meshed together with the theory of what was happening and what we observe here on Earth. Let's see here. Back. Yeah.
What about the dispersal of these elements? If these are relatively rare events, and all of the rocky planets that we see are made up and composed of all these elements, is it simply gravitational pull that brings these newly formed elements into a place where they can actually condense and form a planet?
Also another great question. So the question was, how do these materials that are created in the explosions, how are they actually dispersed outwards so that they can then later form into other planets? This is also another area of very active research that there's a few other people actually at Carnegie studying in detail. In particular, the question is, so supernovae are sort of happening everywhere, and this material, again, it's flung out at intense speeds. So sort of very quickly you start to have certain patches of their sort of region around them that have these elements flung out in them. But if neutron-star mergers are much rarer, then they're just going to be much more of them in very consolidated areas. So this is something that people are spending a lot of time, for instance, looking at sort of pristine sets of stars to sort of understand sort of how much of that material is in different places or how consolidated is it and whether this all makes sense together. So we know it's thrown out there. We don't know yet if it's a problem, that whether or not we need something besides neutron-star mergers for that reason. Yes?
When you had the diagram of the periodic table, you showed the illuminated part down through iron. All the rest of the periodic table are requiring neutron-star mergers to create all of that matter. If neutron-star mergers are so rare, how come we have so much of all of the rest of the table of elements? There seems to be a problem there with having very, very rare events creating significant amounts of matter.
Yeah, so the question was, is there a problem with having rare events like neutron-star mergers? Can you actually create all of those heavy elements that we see? It turns out, I mean, we don't know for sure yet. We have now seen one of these events where we can measure about how much was created. But it turns out that while we do have all of those heavier elements on Earth, they're much, much rarer than the ones that are highlighted there. And we measured for this one explosion about how much material was created, and basically it's fully consistent. So you need something where you need much more material. If neutron-star mergers were going to explain everything, you would need far more material to be formed in each merger than you would if it were supernova, for example. However, the amount of material we measured in this element, in this particular object last fall, it was a lot, actually even more than was expected. People are now actually worried that you could get too much from neutron-star mergers compared to what we observed. That's now the direction we're actually going. So it's still uncertain, though, because we've only measured how much was created in one event. So sort of next year, so January 2019, LIGO is going to turn on again. And it's expected that there should be a handful more events over the year that we will be able to observe. And we'll be able to start piecing together whether this event produced more than is average or whether all of them are actually producing that much, in which case we might have a problem in the other direction. Yes.
Two questions, if I can. Sort of related to that, how recent is the idea that most of those the old elements, whatever most supernova elements, have forming neutron-star mergers? Because I'm picturing that sort of glass wall of the sort of particles describe where each element comes from, and I don't remember anything about neutron-star mergers.
The original theory of it is actually not that new. It was proposed, I'm trying to remember if it was the 40s or the 60s, the original paper that proposed this could be a way, but sort of things ebb and flow in terms of popularity and also whether it's necessary. And so it's been known for a while that these mergers could hypothetically produce the physical conditions necessary, but it was not yet understood, like, how common are they actually? Also, do supernovae have a problem or not? And I do want to emphasize with this too, what this measurement showed is we definitely know that some of these heavy elements are made in neutron-star mergers. This, in itself, this one object does not rule out that also supernova and other types of explosions can also contribute to it. That's definitely now a ton of research is being done in that field right now. But yeah, it's been hypothesized for a while that this could be possible. Yeah, I was definitely going to look that up. Those might be ones that are not naturally occurring, and so are only created here on Earth, but I'm not actually sure about that. Yeah. Yes.
Are there deposition records in the geological strata we examine on the Earth? In other words, would you find the incidence of these things in the strata, if you will?
So there are definitely... Yes. So in particular, a lot of work is actually done looking at the abundances of these different elements on the ocean floor. So that's one of the main areas where people look. I'm not sure if there's evidence that this varies as you, like, information, like if the abundance of them would vary. It's more how much is there overall, and then people have looked, by looking at the ocean floor, try to make arguments over sort of when did the supernova that would have had to, or like whatever caused these heavy elements, so either supernova, neutron, when would it have had to occur and to distribute these sorts of things. I'm not sure about that. I don't know.
Let's do one more question.
Okay, yes.
What kind of object was left over after the event?
That's a great question. It was what type of object was left over after the event. We're not positive. So basically, we have from the gravitational wave information from LIGO information on sort of the overall masses of the components that merged. And it's right at that level where it would either be the most massive neutron star ever known or the least massive black hole ever known. There are a couple of ways we can try to get at this. So in the future, LIGO will actually be able to tell the difference. So in the sense that they have signal as the merger's happening, and sort of at certain frequencies, and once it comes down, like once the merger happens, there's this process known as ring down, where like it's one object, but it's sort of ringing down. And that looks different if it's a black hole or neutron star. It turns out for this run, they just weren't sensitive enough at those higher frequencies, whereas they expect to be in future runs. Based on information from the light that we see, our best guess now is that it eventually formed a black hole, but it was something where it was, for at least a few milliseconds, it was a very heavy neutron star, but after a few milliseconds, it collapsed into a black hole. And we can infer that from things like we think we see evidence of a jet, so material thrown out at something like 99% of the speed of light, which you can see in things like X-ray and radio. And in addition, sort of exactly what elements we think we pieced together from this object. It was very blue at early times, but then became very red at later times. Our best guess now is that makes the most sense for a scenario where you have sort of this temporary time period where it's a neutron star and then it collapses into a black hole. But that's something which will be tested as we start to see more events and view them from different angles and with different masses put together.
I know there's a lot more questions. I'm sure Maria will be happy to come on up to answer them. Let me just point out that our open house is October 14th. We've already set that date, so we hope those of you who have not visited our campus will come out for that. And otherwise, we will see most of you again next year. But in the meantime, let's thank Maria for a great talk.
Thank you.